Okay, thank you again for inviting me. This is going to be a chalk talk, not a slide talk. And my goal is to really take a few of the ideas that I introduced last time and go into a little more depth. So a little more precision, a little more depth so you can see how they work, okay? Also, I'll be introducing one or two ideas that will come up in tomorrow's talk as well. Last time I tried to give a sort of overview of what geometric group theory was about, and I also told you a little bit of history. So in particular, I mentioned that Max Dane was working back in around early 1900s on groups that were acting on the hyperbolic plane. All right, and that he was able to show, using the geometry of the hyperbolic plane, he was able to show that these groups had all kinds of interesting algebraic and algorithmic properties. So he used geometry to obtain group theoretic information. So then next there was the work of Gromov back in late 1980s, early 1990s, and what he noticed was that what Dane had used was only had to do with the large scale geometry of H, and that he could generalize this by looking at groups acting on a space with some kind of large scale hyperbolicity. So that's what I want to talk about today. Large scale hyperbolicity, hyperbolic. Okay, so So today what we're going to do first is explain in a little more detail what is large-scale geometry. And I guess on why is it so effective. Okay, so let me begin with some terminology. Actually, before I begin with some terminology, let me begin with some intuition. So we could talk about local geometry and we could talk about large-scale geometry. So the intuition is when you talk about local geometry, or it means what am I seeing if I look up close? I look at a very small neighborhood of a point. What am I seeing? Is it we have all kinds of notions in topology of locally path-connected or locally compact or locally this or locally that. It says, you know, for an arbitrarily small neighborhood, I have some property. Or maybe it's locally an n-disk, so then you're working in a manifold. Okay, so a lot of conditions that we work with in topology have to do with local geometry, all right, or local topology or local geometry. So large-scale geometry is, I don't care what it looks like close up. What I'm interested in is if I stand way back from my space and squint a little, what do I see? All right, so what is this sort of large-scale picture that ignores the local, what's going on locally? All right, so what I want to do is make that precise. All right, I want to say, can we make that notion, that abstract notion of looking at something from far away, precise? All right, so now let me introduce a little terminology. So what we're really going to do is define what it means for two spaces to have the same large-scale structure, the same large-scale geometry. All right? So when we're working with metric spaces and we're talking about geometry, the usual concept of comparing two metrics would be an isometry. Say they have the same metric. They're isometric. Okay? So let's start with isometries, and then we're going to loosen that up so to make it large scale. So so let's just take metric spaces, x, y. These are right now, I'm just assuming they're metric spaces. I don't care what kind. Okay, then we have, let's say f is a map from x to y. All right, then we have the following definitions that everybody probably knows. Well, actually, let me do it in two parts. F is an isometric embedding. If it's distance preserving, if it preserves distance is simply meaning I'm not even going to write it out. Given two things of a given distance, you map them forward, they have the same distance. That's all. All right? So notice that an isometric embedding is automatically continuous and injective. It's injective because two things, you know, aren't zero distance here, then they're not zero distance when we get into here. Okay? So it's automatically continuous and injective. And so if we simply add F is an isometry if in addition it is surjective. Okay? So now we have a bijective map which preserves distances, and so of course its inverse will also preserve distances, blah, 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 blah. Okay, so isometric, two metric spaces which are isometric are the same as far as, you know, we can't see any difference. Okay, so all we want to do is just weaken this a little. All right, so what we want to weaken it is to say the same thing, except it doesn't have to preserve distance on the nose, it just has to distort it not too badly. All right, we're going to allow it to distort distances, but not too badly. So what does not too badly mean? Not too badly in this case means that there's a linear function, basically, that tells you how much distortion there is. Okay, so our next concept is, so as before, so again, x, y are metric spaces. Well, we don't need this here. Let's just go on. So we still have a map from here to here, and we will say F is a quasi-isometry. Oh, quasi-isometric embedding, excuse me. Embedding. So I'm in the same situation, two metric spaces and a map. Embedding. If there exists constants, lambda and epsilon, such that for all x, y, and x, the distance between the image points, so we want to compare the distance between f of x and f of y, so I take 2 points in here, I map them forward, and I want to compare how is the distance in here related to the distance I started with, right? Okay, so here's the rule. It has to be less than lambda times the distance xy plus epsilon greater than or equal to 1 over lambda distance xy minus epsilon. Okay, so the linear function that it distorts, but we have some control over the distortion. All right, and similarly, we have f is is a quasi-isometry if, in addition to this, it's quasi-surjective. So what is quasi-surjective? It means that if, in addition, every let's use the same epsilon. Yeah, let's say every point in y lies within epsilon, and I'm using the same epsilon here, epsilon of a point of the image. So you look at the image, it doesn't quite cover everything in y, but everything in y is within epsilon of one of those points. All right, so the epsilon ball around it, epsilon neighborhood of it is everything.
But it means the distance is small. You don't care what happens in the image.
That's absolutely right. That's absolutely right. Okay, so observation, and we'll see this. We are going to see this with the examples. So we're going to do some examples now. Well, you'll see as we go along, but maybe I'll preview it. That here we said this automatically gives you injective and continuous. This does not give you injective or continuous. All right, thanks to this little epsilon here, we get to ignore a lot of stuff. If it wasn't for that, we'd at least get, you know, some kind of something. But here we could things that could go to zero that weren't before. All right. So we've got it's quasi-injective and quasi-surjective and quasi. I mean, it almost is, you know, things that get identified had to start out reasonably close together, but then they could get identified, and so we've loosened up everything. So let's look at some. One more terminology. So I'm doing a lot of terminology to start because I want to use this later. So I could say this. So a geodesic. So I'm going to be talking about geodesics and quasi-geodesics, and the way to think about these is, before I was talking about a geodesic as the shortest path, but we could also parameterize it. So if we want a parameterized one, a geodesic is an isometric embedding of an interval into a space X. So a geodesic in X, this is an interval. It could be a finite interval, or it could be an infinite interval, or it could be the whole real line. I is an interval, and if I have an isometric embedding of the interval into X, then that or its image, we're not going to worry much about parameterizations, is a geodesic. Okay? So the reason I introduced that is what I really need to introduce as a quasi-geodesic is, what do you think, is a quasi-isometric. So it is quasi-isometric embedding, etc. All right? So geodesic is straight, quasi-geodesic, well, not quite. It can wander a little, it can do funny things. Yeah.
Am I right that this definition R and Z are quasi-isometric?
Yeah, that's my examples. Let's do the examples.
Geodesic is allowed to be discrete?
Oh yeah, yeah. Oh yeah. No, they can be bad. It turns out there are theorems that you can always replace them with one that's continuous, that isn't too far from the original. There are various theorems about taming quasi-geodesics, but an arbitrary quasi-geodesic, yes, can jump around and do. Whoops. Yeah, could look like that. Yeah, they're not very nice looking. All right, and that's gonna come up in this. Okay, so let's do examples, and then you'll really see it. All right. Remark one. One more thing I want to remark before we go on. So we write. So if if there exists a quasi isometry from X to Y, we write this for short, so I don't have to write that out all the time. And of course, this suggests that it must be a equivalence relation, and indeed it is. That's a nice exercise for you to do when you get bored. So exercise. This an equivalence relation. And in a way, the tricky part is showing that there's an inverse. But we'll see that in the examples. We'll think about this in the examples, okay? So it turns out this is an equivalence relation. And all right, so let's do examples. So the first one is exactly what you said. Let's take the integer grid with the taxi cab metric I talked about last time. Okay, so getting from anywhere to anywhere means you travel along a path in the grid. So okay, and so this is just the grid, and I want to include it into the plane with the standard metric. So now I'm in the plane. So the distance between 2 points is the Euclidean distance. Yeah, with the standard Euclidean metric. All right. So I have an inclusion from here to here, and it does not preserve distance. All right, it does not preserve distance. So, I go from here to here. Here I have to travel like this, but once I've mapped it, this thing into here, now I get to travel like this, right? So it's definitely not distance preserving, all right? Okay, but it turns out that it doesn't distort distances by too much. In fact, you can show that this is that you can take. This is what's called a root 2 0 quasi-geodesic, that you could take lambda to be root 2 and epsilon to be 0 in this case, and check that that this is Okay, so that I claim this is, and clearly every point in here is bounded distance from points in here. Sorry, if I want to use the same epsilon, this is a little messy. You could take this to be a different epsilon if you want. Sometimes you take it to be the same. If I want to take it to be the same, I probably need epsilon to be 1 here to make it quasi-surjective, to make every point to be within 1 of the okay, so this is you can check easily that this is a quasi isometry going this direction. So it's got to have an inverse map, right? What's the inverse map? Got to be an inverse. Well, here's where it's important to remember that these things don't need to be continuous. So what are we going to do? We're going to take think of this as sitting in here. So for each, we have to somehow send the inside of this out to the grid. So basically, forget the middle point for a second. Just send everything out, to sort of just send it outward, and then arbitrarily decide where to send that middle point. I don't care, just anywhere. The point is, you need to send this whole square to the outside of the square. All right, it's not going to be continuous. There's no way. All right, but it's not. Things aren't moving too far. Things that whatever distance they were before hasn't changed by that much. There's control over how much it's changed. Okay. All right. So that's a quasi isometry. Let's do. Here's another one. So let's do another example. Just to show you. You already see it here, but this is. Let's suppose X is a tree, an infinite tree, or maybe a 3-valent tree, or take your favorite tree, I don't care, and keep going forever, okay? And now let's take Y. I'm simply going to take each vertex and replace it with a sphere, all right? So I'm going to draw the same tree, but now I put little spheres on each. Everybody got the picture? A little two-sphere, all right? Okay, it's not hard to see that these are quasi-isometric. In this direction, it's obvious. You just collapse each sphere to a point. And in the other direction, okay, well, somehow when you go here, you've got to get here and then here. There's some way around. You can find a way around. There's clearly a map that you can get backwards. That's a good question. If we take each edge to be length 1, all we have to do is, these can be unit spheres, and then you take the path length metric. So we're always taking, I should repeat that. So I said this yesterday, but I should repeat it today. All our metrics are called our geodesic metrics, meaning we always take the minimal path length to be our metric, always. So in this case, we have to say how big these spheres are. I'll just take them to be unit spheres and take the edges to be length 1, and then you just take minimal path length, always, okay? Okay, so there's an obvious collapse map, and there exists a map in the other direction. And the only reason I did this, this example, actually both of these examples, is you think about, again, the intuition. So one observation here is the fact that the topology can change completely. You can have all kinds of homology here, et cetera, et cetera. So we're not preserving any kind of topological invariants are not preserved by this property. All right, we're preserving something about the metric, but not the topology and not the local geometry and not the, okay? All right, so in both cases, again, intuition is if I stand far enough back, they kind of start to look like each other. You can't really see the differences anymore. All right. Okay, so now the most important example, and the one we actually care about. We're interested in using metric spaces to study groups. And I said one class of metric spaces we do that with are the Cayley graphs that I talked about last time. So the third example is if G is a group, it's a finitely generated group. And supposing I want to build a Cayley graph. So I described how to do that in the last lecture. I'm not going to give the whole definition again, but basically the vertices are elements of G, and the edges correspond to things that differ by a single generator. All right, so I observe that different generating sets give different graphs. All right, so supposing I have a generating set, so S1 and S2 are two different generating sets, finite generating sets. Then I claim, so first of all, then, there's a natural map. So let's see how this works from the Cayley graph of G with one generating set to the Cayley graph of G with another generating set. So what's the map? Well, on vertices, a vertex labeled by an element of G goes to the vertex labeled by an element of G. So on vertices, it's just an identity map, all right? But the problem is in here, I have G1 and G2 are related by an edge if and only if this is true, right? But what if S is not in here, all right? So this is S in S1. But what if S is not in S2? Then these two elements appear somewhere, but they're not connected by an edge, all right? So what do? What I do is I take this element S and I write it as some product of elements in S2. That gives me a path from here to here. It's no longer a single element in S2. It's some product of elements in S2. And I map this edge to that. Right? And I do this everywhere. Every time I see an S edge, I take this new expression and rewrite it as that. All right? And you check that that is a quasi-isometry. And the map in the other direction is obviously, you do the same thing going the other way, and you can check that this is a quasi-isometry. This is a quasi-isometry. Okay, so this is good news. What it says is that two Cayley graphs have the same large-scale geometry. All right, so looked at from far away, they look basically the same. All right. In fact, you could say a little more than that. There's a famous theorem in geometric group theory. Known as the Milner-Schwarz lemma, but it's a theorem. I guess I could call it a lemma. So Milner Schwarz. Proved independently back in the old days before there was archive and you always knew what everybody had done right away. And it proved different times at neither of them knew about the other. Okay, so the theorem says that if we have two actions, so if G, a group, acts geometrically on two geodesic metric spaces, X and Y, then X is quasi-isometric to Y.
Geometric means what?
So I gave a technical definition of this last time. It's by isometrically, properly, and co-compactly. Doesn't matter if you weren't here last time and didn't see those. It doesn't matter. Just acts nicely. Has a nice action, a well-behaved action on two different metric spaces. Then the metric spaces are quasi-isometric. All right. So that's why, from the point of view, so in particular,
So G and X are quasi-isometric itself.
well,
That's it.
that's right. In particular, it's X will be these will be quasi-isometric to any Cayley graph for G.
That's correct.
All right. So anything that so for example, if G acts on some other space that isn't the Cayley graph, that other space will also be isometric to the Cayley graph. All right. So they're all quasi-isometric to each other. So in particular, the important point about this is any property, any geometric property preserved by quasi-isometry is intrinsic to the group. becomes a property of the group. All right, it's now intrinsic. It doesn't depend on what I choose to act on or whatever. It becomes a geometric property of the group in some sense. All right, we can talk about a group being hyperbolic or being, whatever this property is. All right. Okay. So so that was all about what is large-scale geometry. By large-scale geometry, I mean geometric properties that are preserved by quasi-isometries. All right, that's when I refer to some large-scale property, that's what I'm talking about. And we're looking for properties that are preserved by these quasi-isometries and therefore are intrinsically properties of the group itself. Okay? All right, so yeah, that was your introduction to large-scale geometry. Let me make one remark, actually. Before we go on, so the next part of the talk is going to be about what can we then learn from these properties once we have them. But before I do that, I want to make one remark, which is supposing remark, if H is a finite index subgroup, then then I claim that H is quasi-isometric to G, or if you don't like that notation, the Cayley graph of H is quasi-isometric to the Cayley graph of G. We sometimes talk about G itself as a metric space because we can identify it with the vertices in the Cayley graph and just take the metric given by that. So if you don't like this, say Cayley graph of H is quasi-isometric to Cayley graph of G. All right? That's not hard to show. The easiest way is to pick, I guess I also want, is to pick your generating set here and then just expand it to be a generating set here, and then you get a natural map from the Cayley graph to the Cayley graph. It's an exercise. It's not difficult to show, all right, that these are quasi-isometric. They differ by finite index subgroup. One of the sort of, I guess it's sort of a meta question, sort of background questions in geometric group theory, is to try to classify groups up to quasi-isometry. Which groups are quasi-isometric to each other? All right, well, here are some right away. Anything finite index is automatically easily going to be seen to be quasi-isometric. But what else? Is there more? Are there other types of things? So I'll call this sort of a meta question. It's been answered, so classify up to quasi-isometry. So this has been, people have thought about this a lot for certain classes of groups like Coxeter groups and various types of well-known groups, and there's some partial results known, but there's a lot of it's still very much not known in general which groups are quasi-isometric to each other. All right. So one of the questions you might ask is you have two groups, G1 and G2. Maybe this has a finite index subgroup H1 and a finite index subgroup H2, which are isomorphic. So if that were the case, then this would be quasi-isometric to this, would be quasi-isometric to this, would be quasi-isometric to this. So there's a name for this. These are called commensurable groups. Two groups are commensurable if they have isomorphic subgroups like that. These are finite index subgroups. And so there are parts of these questions are sometimes we call them rigidity questions. Are the only quasi-isometries these commensurabilities? Is that it? Is that the only ones that are quasi-isometric, or are there other groups that are quasi-isometric for less obvious reasons? All right, and so these are all big questions in geometric group theory that are really interesting, and some people here in the audience have looked at some of these questions. So, yeah. Okay. So any questions on that? That's sort of the introduction to what large-scale geometry is all about.
So you might want to say that we ignore the finite groups or finite compact spaces, they are quasi-isometric web points.
Yeah, they're all quasi. I mentioned this yesterday. Yes, so finite groups are exactly have a finite index subgroup, which is the identity. So they're all quasi-isometric to the point, to a single point, and so we can't distinguish any of those. Those are not. Yeah, another thing that comes up because of this is that many theorems. You go read theorems in geometric group theory, and half of them talk about some property is virtually true. So that's a shorthand statement for the fact that some finite index subgroup of your group has this property. So you want to say, does G have property P? Well, maybe it does, maybe it doesn't, but we can say that some finite index subgroup of it does, because we can't tell the difference in geometry. If you're working in large-scale geometry, you cannot tell the difference between the big group and the finite index subgroup. All right, so if it's a large-scale property, often the theorem reads something is virtually this or virtually that. Okay, so all right. So what I'd like to do is say, so as I said, the second part of this talk is sort of to explain that once you have one of these intrinsic large-scale properties of the group, what does it do for you? And there are several. We'll see how much time I had. I thought I'd just go back and focus first on hyperbolicity. It's not the only large-scale property we study. There are a lot of other interesting things like growth functions and all kinds of interesting things that give you other properties. And I may have a little time to talk about that at the end. But let's spend some time talking about hyperbolicity first. And if possible, I'll give you some other examples later. Okay, so back to hyperbolicity. So the first claim is, so the first question, you're given a property, a geometric property of a space, and the first thing you want to know is it preserved by quasi-isometry? Is it a large-scale property or not? So for example, in those examples I gave you, having some non-trivial, say, second homology, that's not preserved. I mean, so what properties are preserved by quasi-isometry, by this process, all right? Which properties are large-scale? So all right, so let's recall what hyperbolicity is. So, so a geodesic metric space is delta hyperbolic. This was the idea of hyperbolicity that Gromov introduced. If every triangle, let's give it a name, X, if every triangle in X is delta slim. And what does delta slim mean? I'll just draw a picture. Delta slim means that any point on any other side is within delta of one of the other two sides. Or equivalently, if I take the delta neighborhood of this side, it's not going to work the way I drew it, and the delta neighborhood, oh no, of this side, then this has to live totally inside the union of those two delta neighborhoods, okay? So every point is within delta of either one or the other of the other sides, right? So we got thin, 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 and just a little delta-sized wall in the middle there is all we get, okay? All right, so that's hyperbolicity. And so the first thing, let's see how this works, is to show that this is preserved by quasi-isometries. So let's see how this works, because, yeah. So I think this proof gives a lot of insight into some, and also brings up some ideas that I'm going to use tomorrow. All right, so theorem. So I'm not going to prove anything in vast detail. I'll just give you an idea of how these proofs go. So theorem, if X is quasi-isometric to Y, then I claim X is hyperbolic. Sorry, if I just say hyperbolic, it means there exists a delta such that this is true. So sometimes I'll specify the delta and sometimes I won't. So then X is hyperbolic if and only if Y is hyperbolic. So it's preserved. Either they both are or they both aren't. By the way, I didn't put the delta in here for a reason. The delta that works for this won't necessarily be the same delta that works for that. Okay, there'll be a delta, but it won't necessarily be the same one. All right. All right. Let's try and prove this. Let's see what would be involved in this. Okay. So we start out and we say suppose. So we're assuming they're quasi-isometric, and suppose x is hyperbolic. And we want to prove that then y has to be hyperbolic too. All right, so we have quasi-isometric. And so let's take a quasi-isometry. And I want actually to take the one that goes this way. So let f mapping y into x, because I want to start with the triangle here and push it into x and say I'm going to use the thinness of this to get thinness. Okay, be a quasi-isometry. Okay, so let's draw a picture. We're in y, and our map f takes us into x. And I need to show that triangles in here are slim for some delta, right? So I take a triangle in here, ABC. Right? And I don't know anything about this triangle. So I hit it with f and push it forward. All right, so I've got an f of A, f of B, f of C. Okay, but now this was a geodesic. Right? A geodesic, remember, is an isometric embedding into y. But now I've composed it with f. It's no longer an isometric embedding, but it is still a quasi-isometric embedding. In other words, these become quasi-geodesics. Okay? Those become quasi-geodesics. Right? So let's label this. So if I just call this thing the triangle of ABC, triangle with ABC vertices, this is f of the triangle ABC, right? This is what happens when I just hit the triangle with f, yeah? Okay, that I don't know much about that guy. What I do know something about, oh, look, colored chalk. They asked me if I wanted colored chalk. Why not? What I do know something about is triangles made up of geodesics. So this is a geodesic metric space, meaning any 2 points can be connected by a geodesic. So I'm going to connect these by geodesics. Yeah, they exist, so I'll just find them. And this guy's a little different. What is this guy? Well, let's call this guy the triangle spanned, the geodesic triangle spanned by f of A, f of B, and f of C, yeah? As opposed to this thing. All right? This is the triangle spanned by a triangle spanned by those 3 points. All right. All right. I know this guy's delta slim. All right. So let's say let's make him delta. Sorry, I should have given you a delta for this. All right. This guy's delta slim because I'm assuming x is hyperbolic. Yep. So I know this triangle's thin. How can I conclude that this triangle's thin? Well, in order to pull myself back, I need to know something about the relationship of this to this. I need to know that this guy isn't really all that different from this guy. And then I'll be able to pull the information back. All right? So the key is to understand, compare a quasi-geodesic between 2 points to a geodesic between 2 points. All right? And it turns out that's a key property of well, before I say that, so we need to understand how quasi-geodesics are related to geodesics. All right, between the same 2 endpoints. All right. Well, let's look at an example. Okay, this isn't hyperbolic. There's a good reason I'm giving you an example that's not hyperbolic. So in the plane, which is not hyperbolic, all right, what can happen? Well, it turns out that these things that taking any line here, that's a geodesic. These, and taking the right triangle that joins those, this is a root 2, 0 quasi-geodesic. All right? So by taking bigger triangles, there's no way I can keep this quasi-geodesic close to this. It just gets us farther and farther and farther away, the bigger the triangle is. I can't control in R2 how far away a quasi-geodesic gets from a geodesic. So the key property of hyperbolic space that makes everything work is that in hyperbolic space, quasi-geodesics stay close to geodesics. That's like the fundamental property, all right, so let's write this down. This is the so key property. So, of course, this is not hyperbolic. So, because in hyperbolic spaces, key property of hyperbolic spaces, which I'm not going to prove for you, but I'm afraid this one you're going to have to just accept, is called the Morse lemma. And I think I'll write not, so suppose S is, suppose X is hyperbolic, then quasi-geodesics stay bounded distance. This is a very vague statement. Bounded distance from geodesics. And let me draw you a picture of what I really mean, rather than write it up in complete formality, which takes too long. Okay, what I really mean is given any quasi-geodesic, so quasi-geodesic, a lambda epsilon quasi-geodesic, meaning those are the, if you go back to the definition of quasi, you always get these two, lambda and epsilon, that determine your function. So given this, if I straighten it, then the distance from here to here is less than or equal to n, so there exists n, which is it does depend on lambda and epsilon. So I get to have a different n if I change the lambda and epsilon. But for a given lambda and epsilon, there exists a fixed n, so that the distance is always from here to here is bounded by that n.
And the geodesic, because the geodesic
No. Oh, yeah, it doesn't for any geodesic. It doesn't matter for any geodesic. It's bounded distance. Yeah, all that matters is how quasi this is. It doesn't matter. The geodesic, yes, geodesics are not unique. That's correct. Okay, but intuitively, it's the way to remember what this says is just that quasi-geodesics stay bounded distance from geodesics. All right, so the bound does depend on the lambda and the epsilon. But all right, so let's go back. So now we're back here. Yeah.
You say n of lambda, it's something complicated, or it can be written explicitly?
You mean the actual describe n?
Yes.
There are estimates. I don't even remember what they are. Nobody uses them. I can't remember off the top of my head.
It's polynomial?
depends on delta.
Yes, that's right. I mean, that's actually more important. It actually depends on delta. Yes, you're right. It also depends. I guess I was assuming it depends on the delta as well. That's right. Sorry. I was assuming we have a fixed hyperbolic thing, and now we're taking
The right formulation is if you have x with delta.
delta hyperbolic, and this will depend also on delta. I was assuming delta was a fixed given. We're just working in one space. But you're right. It also depends on delta. But here I need to put this in because even in the same space, without changing the space, I could change the type of quasi, and then I have to. So don't worry about this. It's not. I mean, yes, we can go for more. I was trying to avoid being too many quantifiers, etc. So the point is fix the space, and in our case, we get to fix the lambda and epsilon because it depends only on on f. The lambda epsilon depends only on the lambda epsilon for f. So all of these are going to have the same lambda epsilon. There's only going to be one delta involved, the delta for x. So all of that stuff's going to be fixed. all right? The lambda's fixed, the epsilon's fixed, the delta's fixed. So for us, there's just one n that we have to worry about. That's the point. For our picture, there is an n that always works here, all right? There's just a constant n, right? So it says that all of these, there exists this n, so that all of these never get farther than n away from here, all right? A fixed n now, independent of anything else.
Does it matter like how you parameterize this?
No, because now I'm just looking at the image. I'm not looking at particular points. I'm just saying it's in the n neighborhood. It lies in the n neighborhood is all I'm saying. I'm not saying that the parameterized points are with. You can worry about parameterizing too and write down theorems for that, but right now I don't care about that. I just care that it lies in the n neighborhood, okay? Yeah.
This n plays the role of epsilon?
Of epsilon?
Or it's irrelevant?
You mean the epsilon? No, this is really something else. The epsilon was this. The epsilon I'm using here was just how quasi this is, and it will play a role in determining n. But I don't want to worry about that. I just say there is an n that works. Period. For this entire picture, no matter what I start A, B, C with, no matter what how I straighten to whatever, the same n is going to work for the entire picture. Okay, that's what matters here. Okay. So now we can come back to our picture and keep going. All right. This is the key thing we need. And as I said, if anybody's still with me tomorrow, the Morse lemma is going to be central to what I'm thinking about tomorrow. All right.
You'll tell what is in tomorrow.
Sorry. Oh, I don't know. All right. We'll talk later. Okay. So. We're basically done now, so back to the proof. To proof of theorem. All right, so we now have so let's say right. So we now have that x is delta hyperbolic. Implies that the triangle spanned by f of A, f of B, f of C, that is, say, the purple triangle in here, all right, is delta slim, because all triangles are delta slim, all right, which implies that, well, I'll write it as slim even though it's not a triangle, but it's the same thing. So we take f of T, A, B, C, which means our squiggly triangle here is not delta slim, but it's delta plus 2n slim in the sense that every point on this side is within delta plus 2n of one of the points on the other side. Same thing. So we go to here, then we go delta to another side, and then we go to here. But so n, delta, n, that's all. We're on the other side, okay? All right? But that implies we know that f doesn't distort distances too much. F is a quasi isometry. Lambda, say a lambda epsilon quasi isometry, then that implies that the distances here could only be worse by lambda plus 2f. It can't be distorted by too much. So we get that therefore the original triangle is delta prime, which is I think lambda times delta plus 2n plus epsilon slim. Just the distortion. So however much f can distort the distances, right? It's bounded. All right. So the point is we've got a new delta, but we've proved that every triangle is delta prime slim now. Okay. Okay. So yeah. Okay. So what we've proved this theorem that hyperbolicity is a large-scale property. In particular, it makes sense to talk about a hyperbolic group. What's a hyperbolic group? It's a group which acts geometrically on a hyperbolic space. It doesn't matter if it's the Cayley graph. It doesn't matter what space you look at. If one of them's hyperbolic, they're all hyperbolic. All right? So, so let's say so define G is a hyperbolic group? Well, we can define it any number of ways, if and only if some, hence every, Cayley graph is hyperbolic. Or maybe we don't want to work with the Cayley graph. Maybe we have a group acting on the hyperbolic plane or hyperbolic end space. Maybe we don't have any idea what the Cayley graph looks like. All right? So we could also say G acts geometrically on X, where X is hyperbolic. Any space you want. Sometimes they come to us in some other form because they're acting nicely on some nice hyperbolic space. We don't have to look at the Cayley graph if we don't want to. It doesn't matter. They'll all be they're either all hyperbolic or none of them are hyperbolic. Okay? Yeah? So that's the advantage of large-scale properties, is they really become intrinsic to the group. Okay, any questions about that? Okay. I'm almost out of time. All right. The other thing I wanted to do, what time am I in? 5:15, I think. All right. Okay. So the other thing I wanted to give you an example of, so this was sort of honing in on what large-scale geometry means and why it's useful in geometric group theory. I was hoping to give you a little bit of an idea of, once we have one of these properties, how do we get something algebraic out of it? How do we translate that into a property of the group? So let me give you, I won't be able to give any details, but that's my last. So the claim was that geometry could tell us about the group theory. So, so how do large-scale geometric properties imply more algebraic or properties, or in this case, combinatorial properties of the group of a group. All right. So I thought. So last time I had a slide where I gave a long list of properties that hyperbolic groups satisfied. I said, if you know it's hyperbolic, then it's this, 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 this. So I thought, to give an idea of how you get to those, I'd do the one that sort of spurned the whole field, which is the word problem, the solution to the word problem. So, so theorem, let G be a hyperbolic group. And you'll see where these kind of properties come in here, too. S, always finite generating set. Finite generating set. Then there is a linear time algorithm. A linear time solution to the word problem. Solution to word problem. So remember, what does that mean? So what it means is, i.e., a linear time algorithm to decide if a word W in the free group on S represents the identity element in the group. Or, phrased another way, in the Cayley graph, if we start at the identity and follow a path which is labeled by this word, will we end up back at the identity again? Is it a loop or is it not a loop? Right? So the word gives me a path, and I want to know, does that path end back where it started or somewhere else? Okay? All right. So let me give you just an idea of how hyperbolic geometry gives rise to this. All right?
And whose theorem and what year?
Okay, so so this is what Dane did this for groups acting on the hyperbolic plane, and then Gromov in 89, 80, I don't know when the paper was published, did it for this more general. Yeah, this theorem, as stated, is Gromov in the early 90s.
Abramovich uses then machinery or IT?
Sort of, yeah. I mean, he was inspired by them, yes, but it requires somewhat different arguments in this general case. But he was certainly inspired by what Jane. That's what got him started on
I
this.
just was wondering whether you can reduce it for them. Because
No.
of the quasi-isometries.
No, you can't. Not every hyperbolic group is quasi isometric to the hyperbolic plane. I mean, there are lots of other hyperbolic groups that are, not quasi isometric to something else, a tree or all kinds of other things. Okay, so just quickly on the idea of the proof. All right, so here's what the first step is. So let X be the Cayley graph. We're going to work in the Cayley graph. I first need to define a K-local geodesic is a path such that every segment of length K is geodesic. All right, so if you look at little pieces of it, it's geodesic, but you don't know that it doesn't eventually come around and it's not geodesic anymore. All right. Okay, so all right, so the first step is to show, and this part I won't be able to explain in any detail. So first show that every K-local geodesic in X is a quasi-geodesic. And not only that, the lambda epsilon depend on just on K and the delta for X. So just a standard. So this is, I don't have time to prove this, but this is sort of believable. It's sort of almost geodesic. It's geodesic for a long time, and okay, it doesn't quite stay geodesic, but one can prove that it is actually quasi-geodesic. Okay, it's not too badly off being geodesic. All right. Okay, so we're going to have to believe that one. Once we've shown that, that's the key. So now suppose we have a path, a word. So now say that W does represent, supposing we had something, corresponds to a loop, and I'll give it a different name, a loop gamma sub W in the Cayley graph. So that's what I'm trying to decide, does it or doesn't it? So let's say it did. What would we see? All right? What would it look like? All right? Well, there's two possibilities, and either it is K-local geodesic or it isn't. The great thing about K-local geodesic is that's a finite, bounded amount of stuff we have to look at, is sort of things of length K. So either gamma W is K-local. All right, it's possible. All right? But if it's K-local, then it's quasi-geodesic. That's what this said. But if it's quasi-geodesic, then it stays bounded distance from the geodesic. Well, wait a minute. I'm looking at a loop. What's the geodesic between the endpoints is just this point. There is no, that means the entire thing stays some bounded distance from it lives in a little ball of radius n, okay? So implies gamma W lies in some bounded ball. We have some canonical, some uniform bound n ball. And in fact, you can do a little better than that. You can actually show that the length of gamma W is bounded. And here I actually do know the constant. It's less than or equal to 8. What did I just do? Oh, I forgot to say. Oh, I forgot a hypothesis. We need K at least 8 delta. Sorry. You need K to be not too small. Yeah. Oh, it doesn't matter. It's just bounded length. There exists a C. It has a uniform bound on how long it is. That's all it gives us. All right. So either it's K local, in which case it's short. It's bounded. Or it's not K local. Well, if it's not K local, then what am I seeing? I ran out of space. If it's not K local, what does it look like? It means that there's some segment. So here's gamma W. It means there's some segment of length less than K that can be shortened. That's not a geodesic. All right? So not K local implies there exists segment of length less than K that can be shortened. So the trick is I'm going to take as my relators short loops, loops of length less than C, and loops of length less than 2K, because I see right here. So here's what I'm going to take as my relators. I have a loop of length less than 2K, right? Because it was less than K and I shortened it. Yeah. And then here I have a loop of length less than C. There are only finitely many words of length less than 2K and words of length C. There's only finitely many labels those loops can have on them. All right? So I have a finite set of relators, which I claim tells me everything. All right? So sorry, I'm over time, but I'm really just about done. Take R, this is going to be the set of relators, to be the set of words in Fs of length less than the max of C, C or 2K. All of those and all of these. All right, take all of those, and what I get now is I take my word, I'm given a word, and I want to know, is it a loop or is it not a loop? So now start with an arbitrary word. I don't know, is it a loop, is it not a loop? All right? Well, all I have to do is, if it were a loop, either it would already be in there. I mean, it might be already in there, and then I'm done. I look at my relators and say, oh, yeah, that's a loop, it's in there. Or maybe it's not in there, but maybe I see a segment that looks like this, and I can shorten it. So if I see a segment that looks like this, I just replace it with this, and I start again. I say, okay, is my new thing in there, or is it not in there? All right? And I just do this, over and over again, and one of two things ends up happening. Either my entire thing ends up disappearing to a point, and I'm done, it's a loop, or it doesn't. I get to a point where I can't shorten it anymore, and then the answer is, it's not a loop. Done, you're done. So the point is that every word that is a loop has to have either one of these or one of these in it. And if it doesn't, it's not a loop. That's your answer. All right? So that's your answer. So this gives you, I can't write this out, but it gives you, it turns out, a linear time algorithm to answer the question, is it a loop or is it not a loop? Okay, so sorry I went over there. Tomorrow we're going to talk about brand new stuff. This is all old stuff. It's all in Gromov and, So thank you.